Thank you for letting me speak. Perhaps thank you. So it's a funny thing to see these limits of graphs, where graphs are combinatorial objects and limits are in analysis. When I started university in '66, we had 11 classes of analysis per week and no combinatorial classes at all. And this now changed a lot. It was so in '66, and now today it is I don't know what. Okay, so what one would like to see, if you want to have limits of something and this kind of stuff, then you want to have a metric space where you can work with them. So the next question is that what is the distance of two graphs? Because it is, you can define many ways. I just show you one example. Perhaps I sit down because I am old and tired. So distance of two graphs, how can we do compute that? If we have the same under node set, so on the same node set, same numbering and different edges, then it's not so hard. We will pick two subsets of the node set of G and compute the edges between S and T in the first graph and minus the second graph. Take absolute value because it is nicer to work for distance. It is nicer to have non-negative numbers. And by later it will turn out that I want to divide by n squared for purposes, and this is the cut distance, and we take this amount here and take the maximal ST, which gives then the cut distance of G and G prime. Now, what happens if we have two graphs with the same number of nodes, but on different nodes? Then we do the following. We try to find the best overlay of the two graphs and take the minimum, the best overlay, which gives the minimum cut distance.
What is n squared in the first distance, the cut distance?
Yeah, what is below the number of, I should have, I don't know why this, oh yeah. So anyway, the number of nodes in VG is n. So this is all the points, and there are n squared over 2 possible edges, and we are working in this huge domain from 0 to n squared over 2, and we call it.
You say node instead of vertex.
I will mix it because wherever you are, they like to use. Some people like to use nodes. Some people like to use vertices, and try to remember that these are the same in my short talk. So when we have the same number of vertices n, then we do find the best overlay for the cut distance, and which gives the minimum cut distance, and this will be the distance in that case. Now, if we have different number of nodes in G and G prime, then we do this little trick that we blow them up. Like a blow up, the nodes behaves like every node is replaced. You don't see my arrow. This yeah. So we replace every node by k different nodes, independent, and but these k nodes are connected every other nodes as in the original graph. You see it on the picture. Now, this way we can compute the cut distance of G and G prime, and the cut distance of G and G prime will be the limit when k goes to infinity of this cut distance. Okay. Now, for instance, if you consider the Erdős random graph with 1/2 constant, the cut distance of n half, and so you take an edge with 1/2 probability. All the edges you take with 1/2 probability, and you consider two random graphs with 1/2 probability, then their distance with, will go to little o1 when n goes to infinity with high probability. And this can be, you can feel it from this if you think about the definition of cut distance and using law of large numbers. One can also show that for different n and m, this will go also to little o1. Another example, you take an edge, and you take the simplest possible case for two graphs, an edge and a path of length 2, so 3 points and 2 edges, and then you do this blow-up business, and you can easily see that this will go to 1/6. Now we want to go further. What does it mean?
I didn't understand the last thing.
So you have an edge, you have a path, it's 3 points.
Formula. You have an edge?
I have an edge.
What?
K2 is the edge, sorry.
Oh, K2
And
is the edge.
P2 is the path of 2 edges. And then you do the blow-up business, and you can compute that this will go to 1/6. Now we have kind of familiarized us with the distance on graphs, cut distance on graphs. So now we would like to define what does it mean that a graph sequence is convergent. So I consider all the homomorphic images of f into G, which preserves the edges. So homFG means the edge preserving maps, and below is all the maps of F into G. Yes?
Does a map just mean a map on vertices?
Yes,
This
yes.
happens to, if there's an edge here, there's an edge there.
There, then it is.
There's no map on edges.
I mean, there is only one single edge or no edge between two nodes. So,
What do you mean there's only one edge between, by definition?
in my case, where I am working, all these graphs have simple. These are simple graphs.
Okay. There's only one edge.
One edge,
Okay.
and so we were. This was the beginning of this whole business, and first you try to work the simplest case. Now, so this TFG, the density of F in G, is defined like that, and we will use this for the convergency. Sequence of G's is convergent if for every F the density of F in Gn is convergent. Since these are numbers, we know what does it mean that they are convergent. So, example, the random graphs. Any F mapped onto 1/2 random graph goes to 1/2 to the number of edges in F with probability 1. Now, now we go to take an arbitrary graph. It is one edge or no edge between two nodes, and we take the adjacency matrix of this graph. It's a matrix, n by n matrix with 0 ones. It's since there are no loops, in the diagonal there are zeros, and where you have in the ij's position, you put a 1 if I and j nodes are connected. Now, instead of this almost non-visible matrix, I take a pixel picture and an n by n square, and divide this into n squared little squares. And wherever in the matrix AG there was a 0, the value of my function will be 0, and it is white. And wherever there was an edge in the ij's position, I put a whole black square, and the value of this function in this whole little square will be 1. So now we have a graph G, and we have a 0, 1 valued function on the unit square, and we are now we can be now in analysis in some sense. Just to show you some examples, here is the so-called half graph, which is a bipartite graph, and half points are above and half points below, and every edge is leaning or vertical. So vertical or leaning to the right, right? Then this has this pixel picture like this, And when n goes to infinity, it will go to this picture. Now, another example, if I consider the random graph on 100 nodes, say, we have this kind of pixel picture, and as n goes to infinity, it will be a kind of constant gray with 1/2 value. Now, if I take this chessboard on n by n square, will this converge to this also gray function with 1/2 value? I am not quite sure. So if I reorder the nodes, it will go to this. So I cannot be sure until I do a lot of work that what is really the limit of such a W until I do all the rearrangements of rows and columns and try to figure out what do they give. So the limiting object, we will call it graphon, is a symmetric measurable function, and for a W graphon, we can compute the density by doing this beautiful integration. And one can easily notice that the density in this graphon business of a simple graph G, we compute the WG, the density of WFG, and it will give what the limit gives for Gn because of this computation. Now, here now I am able to give you two definitions for convergency. If a sequence of GNs goes to, for every F graph, the densities go to a certain density, then we call them convergent. Another one, we love Cauchy from our analytic studies. Gn is convergent if the cut distance delta is Cauchy in our metric, which we defined.
That's the min-max metric?
Yes, yeah, this is the min-max metric, which was in the previous slides. Now, what comes next? We would like to show that these two definitions are equivalent, and one can do this. Before saying something about the proof, I want to show that with the first definition, the random graph with 1/2 probability goes to this one above. I don't want to say this in English. And since the distance of two random graphs go to 0, so therefore we have this probability.
Right, the
And-
notation, what's the bottom one? That's a rectangle instead of a square.
Yeah, it's by mistake.
Same?
Yes.
That's-
So sometimes there is enough fine
You have to explain
little.
it. I'm very sensitive to the shape.
Yeah, yeah. Yeah, life is hard for.
Yeah, right.
Yeah. Especially for. Anyway, I don't want to say anything politically incorrect thing. So just some remark that why are these two definitions equivalent. So there is one direction comes from the counting lemma, which is one lemma around the Semeredi regularity lemma, and but in this form it is good for us. So again, this ugly rectangle is a square.
What does T mean? I forget what T means.
T is the density. So so if
F and G, okay.
okay. Now, so with this we can prove the convergency, and so-called inverse counting lemma is that the cut distance, the density distance of two graphs G and H is less than or equal 1 per k, where F has at most k nodes. And from this, one can also show that for all graphs F with k nodes, the cut distance of G and H is less than 10 over square root log k. One can improve this, but it is enough for us. So summarizing the facts what we have here, I am almost done, that for every convergent graph sequence, there is a graphon in this W set, such that the convergent graph sequence goes to this graphon. And conversely, for every graphon, there exists a graph sequence which converges to this graphon. And another important fact is that this limit graphon is essentially unique up to measure preserving transformations. Summarize.
So for all W, in what sense?
All W in this, it was several slides earlier, all W in
Pictures?
which is on the square, unit square, it is symmetric, measurable. There is a graph sequence which goes to this. So
It's up to measure 0, though.
yeah,
2 or 3.
yes, because yeah.
Okay.
Yeah, and so this means that this W naught is complete by our definition. So we are very happy because we can work with this kind of space very nicely. So this is defined on graphs. Now I will tell you, and I am taking the time of the next speaker, but I think that life is like that. So so randomly drawn uniform attachment graphs, at step n, a new node is born, and any two nodes are connected with probability 1 per n in the new graph. And we forget about the multiplicities, which just ignore the multiplicities of edges. And this will tend to something like that, whatever that says. And one can compute that this graphon, where this randomly grown uniform attachment graph goes to, is 1 minus max xy. The proof goes by computing cut distance. So this means that this combinatorial notion can be used for convergency business. Now, another very nice example. At step n, a new node is born, and we connect every previous node and all its predecessors. We will get this very, very nice, smooth function as the limit. And the question that what can be the limit of this picture, it looks like something like that. What does it mean? I won't write down you the function because I don't. Okay. So this tends to some shades of gray. Is this really the limit? If we compute triangle densities, then it cannot be the same. Where this nice picture goes through. Is this graph convergent at all? Now, if we compute subgraph densities, we can see, I won't compute it for you, we can see that this is convergent. Whether this is, if I rearrange the vertices by degrees, so largest degree is up there, and then it is also a very nice picture, but unfortunately this is still not the limit. And finally, the trick is that we kind of give a representation on the unit square of the points, and there we have so label node born in step k, connecting them to 1 through m, and they are drawn like k per n, m per k in the unit square, and these points are uniformly distributed in the unit square, and we connect 2 points if we have these long inequalities fulfilled, and the limit can be represented as follows. It is an appropriate graphon, and it is 1 if x1 is less than or equal x2, y2, and 0 otherwise, and it gives this nice, beautiful picture. And my last example is my favorite. Start with a single node, and at step n, a new node is created, and it is connected to node I with probability the degree of I in the at that point, plus 1 over n plus 1. And this is similar to the Albert Barabashi example, which was given 20 years ago or so. But our example is dense, so the number of edges is at least constant times n squared. And with probability 1, this graph sequence is quasi-random. So this tends to a constant. But when I do next time the process, it will tend to another constant. So we don't really know when is this constant fixed. Whether, can you tell at the 1 million step that now I know where it will go? So is it possible to predict? So find some distribution of the limits. Okay, so I think I am done, and thank you for your attention.